In this video, we are going to look at the mean value theorem for integrals, the only application we're looking at for the average value of a function this time. Okay, so the mean value theorem for integrals says that if f is a continuous function on this interval between a and b, then there is some number c in that interval. So some number probably in between a and b, some number in the middle of that function interval somewhere, such that the function evaluated at c is the same thing as the average value of the function, which is defined, like we saw previously, to be 1 over b minus a, 1 over the length of our interval here, times the integral of our function. So let's understand intuitively why this is true. If you look at the graph of a function, which is continuous, it must be continuous in order to meet the criteria for this formula. So continuous function means basically you can draw it without picking up your chalk or your pencil. Then the average value of the function must actually be achieved by some middle value. So if I start off with a on the left and b on the right, then there must be some value in between that gets us the average value of the function. So let's just sketch what makes sense to be the average value here, right? We have some relatively high values over on the left and the right, and then some relatively low values kind of here in the middle. So that means if you look at the average overall, it should be somewhere in between the highs and the lows. And in this case, it looks like there are actually two values that meet the criteria for being C here. We've got one right here and one right here. And we know that something like this must always occur. No matter what shape you draw your function in, the middle value there, the average value of the height, must be somewhere in between. It must actually pass through it. So this should feel almost too obvious, right? Based on the ideas that we're thinking of here. Remember, the mean value theorem for derivatives that you've seen previously is essentially talking about this for rates of change, right? We're saying that if you look on an interval from a to b and you look at the derivative of your function at all of the points in the middle, one value somewhere in the middle must have the same rate of change as the average rate of change of the function, right? So just take the word rate of change, the words rate of change, out of the original mean value theorem that you have heard of, and just replace it with function, and you get the same thing for integrals here. So the average value of the function, not the average value of the rate of change, but the average value of the function, must be achieved somewhere in the middle, just like there must be some particular value, right? Again, if we think of the mean value theorem for derivatives here, if you look at the secant line from the right side and the left side here, right? Draw your secant line. What the original mean value theorem said is there's some number in the middle here whose derivative matches up. Right, so you'd get something like maybe here, slightly off. Hard to say exactly, but I'm off on that. Let's see if I can draw this better. Drawing straight lines, the bane of my existence. Here we go. There we go, something like that, right? That there is some particular point in the middle, some particular value here in the middle, which we would then call C, where the rate of change of the function is the same as the average rate of change. Same idea here, the actual value of the function is the same as the average value of the function. All right, so what can we do with this? Well, let's revisit our first example from the last video and see if we can algebraically find this value that we're interested in here, C. So our first example from last time, we were looking at the function f of x equals 1 plus x squared. On the interval -1 to 2. And what we found previously was that the average value here was precisely equal to 2. Again, you can find that by integrating this function from -1 to 2 and dividing by the length of that interval, which is 3. All right, so what does the mean value theorem for integrals say? Well, it says that if this function is continuous on this interval, which it is, then there must be some number in between -1 and 2 here, such that its function value is equal to 2. So what we're saying is there is some number c, so that f of c is precisely equal to 2 in this particular case. And f of c just means 1 plus c squared. So we have 1 plus c squared is equal to 2. Solve for c squared here, we get c squared equals 1, which means that c itself is either plus or minus 1. And both of those happen to be in this interval here. And so you'll remember that when we drew the picture of this, we had a parabola, something like that, with our average value going right through the middle, intersecting at -1 and at +1. So that's exactly what we see right here. And that's all the mean value theorem for integrals says, is that somewhere in the middle, there has to be at least one point that actually takes on the average value of the function. Okay, so that's all that we're going to have for this section here. Relatively short section. Thank you guys for listening, and I will see you again in class.